Critical circuits provide power to essential equipment required for the immediate protection of life and property. These typically include fire alarm and detection systems, emergency lighting, elevator controls, security systems, and nurse call systems. Emergency circuits provide power to equipment that is needed for the safety and well-being of occupants during an emergency situation. These typically include exit lighting, smoke exhaust fans, fire pumps, communications systems, and security cameras. The differences in function are critical circuits are designed to maintain essential functions during a power outage, while emergency circuits are intended to provide additional safety and convenience measures during an emergency. Regarding the power source, critical circuits are typically connected to a redundant power supply, such as a generator or an interruptible power supply, to ensure continuous operation in the event of a grid failure. Emergency circuits may be connected to a combination of grid power and backup sources, depending on the specific requirements of the facility. System design involves critical circuits being designed with a high level of redundancy and fault tolerance to ensure reliability. They often use dedicated wiring, isolation devices, and surge protection measures. Emergency circuits may have lower levels of redundancy and may share wiring with other systems. Code requirements stipulate that the installation and testing requirements for critical and emergency circuits vary based on local building codes and regulations. Generally, critical circuits are subject to more stringent requirements to ensure their reliability and effectiveness. There are some additional considerations such as maintenance. Critical and emergency circuits should be regularly tested and maintained to ensure proper functionality. Facilities should have clear documentation regarding the location and function of critical and emergency circuits for easy reference during an emergency. Coordination is important. Critical and emergency circuits should be coordinated with other building systems such as fire and security systems to ensure effective response during an emergency. To elaborate, critical circuits are absolutely vital for maintaining the immediate safety of a building's occupants and protecting the physical structure during an event such as a power outage or a fire. These circuits are the backbone of life safety systems, ensuring that essential services remain operational when normal power is lost. Let's delve deeper into the specific examples provided. Fire alarm and detection systems are a prime example of critical circuits. These systems are designed to detect fires early and alert occupants, allowing for timely evacuation. They need to function without interruption, even during a complete power failure, because a delay of even a few seconds could have catastrophic consequences. Emergency lighting is another crucial component. These lights illuminate exit routes and stairwells, guiding people to safety when normal lighting fails. They are strategically placed to ensure clear visibility, preventing panic and reducing the risk of injuries during evacuation. Elevator controls are also considered critical. In the event of a power outage, elevators need to either safely return to the ground floor and open their doors or be controlled manually to prevent people from being trapped. The elevator control system ensures that elevators do not become a hazard during an emergency. Security systems, including access control and surveillance, are critical for maintaining order and preventing unauthorized access during an emergency. These systems help to secure the building and protect its occupants from potential threats. Nurse call systems in hospitals and healthcare facilities are essential for patients to call for assistance during an emergency. These systems ensure that patients can communicate their needs to medical staff even when normal power is disrupted. Now, let's turn our attention to emergency circuits, which are designed to enhance safety and convenience during an emergency but are not necessarily essential for the immediate protection of life and property. While still important, they provide a secondary layer of safety and support. Exit lighting, as mentioned earlier, is also part of emergency circuits. While critical circuits provide the primary emergency lighting, additional exit lights may be powered by emergency circuits to ensure comprehensive illumination of all escape routes. Smoke exhaust fans are used to remove smoke from buildings during a fire, improving visibility and air quality for firefighters and evacuating occupants. These fans help to create a safer environment and facilitate rescue operations. Fire pumps provide water pressure to fire sprinkler systems, ensuring that they can effectively suppress a fire. These pumps are critical for controlling the spread of fire and preventing extensive damage. Communication systems, such as two-way radios and public address systems, are used to communicate important information to occupants during an emergency. These systems help to coordinate evacuation efforts and provide instructions to people inside the building. Security cameras can provide valuable information to emergency responders, helping them to assess the situation and coordinate their response. These cameras can also deter crime and help to identify potential threats. The key functional difference between critical and emergency circuits lies in their primary purpose. Critical circuits are designed to maintain essential functions that are absolutely necessary for the immediate protection of life and property. They are the last line of defense against potential disasters. Emergency circuits, on the other hand, are intended to provide additional safety and convenience measures during an emergency. They enhance the overall safety of the building and its occupants, but are not necessarily essential for survival. The power source for critical circuits is typically a redundant power supply, such as a generator or uninterruptible power supply, or UPS. This ensures that these circuits continue to operate even when the primary power source is lost. Generators are typically powered by diesel fuel or natural gas and can provide power for extended periods. UPS systems use batteries to provide power for a shorter duration, typically long enough to allow for a safe shutdown of equipment or a switchover to a generator. Emergency circuits may be connected to a combination of grid power and backup sources, depending on the specific requirements of the facility. Some emergency circuits may be powered by the same redundant power supply as critical circuits, while others may be connected to a separate backup source or even to the grid. System design for critical circuits emphasizes redundancy and fault tolerance. This means that these circuits are designed to continue operating even if one or more components fail. Dedicated wiring is used to isolate critical circuits from other systems, preventing a fault in one system from affecting the operation of critical circuits. Isolation devices, such as circuit breakers and fuses, are used to protect critical circuits from overloads and short circuits. Surge protection measures are used to protect critical circuits from voltage spikes, which can damage sensitive equipment. Emergency circuits may have lower levels of redundancy and may share wiring with other systems. This means that they may be more vulnerable to failures and may not be as reliable as critical circuits. However, they are still designed to provide a reasonable level of safety and convenience during an emergency. Code requirements for critical and emergency circuits vary based on local building codes and regulations. However, in general, critical circuits are subject to more stringent requirements to ensure their reliability and effectiveness. These requirements may include regular testing, inspections, and maintenance. Additional considerations for both critical and emergency circuits include regular testing and maintenance to ensure proper functionality. Facilities should also have clear documentation regarding the location and function of these circuits for easy reference during an emergency. Coordination with other building systems, such as fire and security systems, is also essential to ensure an effective response during an emergency. Now let's consider some specific examples and scenarios to illustrate the differences between critical and emergency circuits. Imagine a hospital during a power outage. Critical circuits would ensure that life support equipment, operating room lights, and nurse call systems continue to function, allowing medical staff to provide uninterrupted care to patients. Emergency circuits would power exit lighting, ensuring that patients, visitors, and staff can safely evacuate the building if necessary. In a high-rise office building during a fire, critical circuits would power the fire alarm system, alerting occupants to the danger and initiating evacuation procedures. They would also power elevator controls, allowing firefighters to use elevators to reach upper floors and rescue occupants. Emergency circuits would power smoke exhaust fans, removing smoke from the building and improving visibility for firefighters and evacuating occupants. In a data center, critical circuits would power servers, cooling systems, and network equipment, ensuring that critical data and applications remain available during a power outage. Emergency circuits would power security systems, preventing unauthorized access to the facility and protecting sensitive data. Let's delve into the technical specifications and standards that govern the design and installation of critical and emergency circuits. The National Electrical Code, or NEC, provides comprehensive guidelines for electrical installations in the United States. Article 700 of the NEC specifically addresses emergency systems, while Article 701 covers legally required standby systems, which often include critical circuits. These articles outline the requirements for power sources, wiring methods, overcurrent protection, and testing of these systems. For example, NEC Section 700.12 specifies the acceptable power sources for emergency systems, including generators, storage batteries, and uninterruptible power supplies. It also sets requirements for the capacity and reliability of these power sources. NEC Section 700.9 addresses the wiring of emergency circuits, requiring that they be kept independent of all other wiring and that they be protected from physical damage. NEC Section 700.4 specifies the testing requirements for emergency systems, requiring that they be tested periodically to ensure that they function properly. In addition to the NEC, other standards and guidelines may apply to critical and emergency circuits, depending on the specific application and location. For example, hospitals and healthcare facilities may be subject to additional requirements from organizations such as the Joint Commission. These requirements may address the reliability and performance of critical electrical systems, as well as the training and qualifications of personnel responsible for their maintenance. Let's now discuss the practical aspects of designing and installing critical and emergency circuits. The first step is to identify the specific loads that need to be powered by these circuits. This requires a thorough understanding of the facility's operations and the critical functions that must be maintained during an emergency. Once the loads have been identified, the next step is to determine the appropriate power source. This will depend on the size and type of loads, as well as the required runtime. Generators are typically used for larger loads and longer runtimes, while UPS systems are used for smaller loads and shorter runtimes. The wiring of critical and emergency circuits must be carefully designed to ensure reliability and safety. Dedicated wiring is recommended to isolate these circuits from other systems and to prevent a fault in one system from affecting the operation of critical circuits. Overcurrent protection devices, such as circuit breakers and fuses, must be properly sized to protect the wiring and equipment from overloads and short circuits. Surge protection devices are also recommended to protect sensitive equipment from voltage spikes. Testing and maintenance are essential for ensuring the continued reliability of critical and emergency circuits. Regular testing should be performed to verify that the power source is functioning properly and that the circuits are capable of carrying the required load. Maintenance should include inspections of wiring, connections, and equipment, as well as cleaning and lubrication as needed. Documentation is also important for critical and emergency circuits. Facilities should have clear and up-to-date documentation of the location and function of these circuits, as well as the procedures for testing and maintaining them. This documentation should be readily available to emergency responders and other authorized personnel. In summary, critical and emergency circuits are essential for ensuring the safety and well-being of building occupants during an emergency. Critical circuits provide power to essential equipment required for the immediate protection of life and property, while emergency circuits provide power to equipment that is needed for the safety and convenience of occupants during an emergency. These circuits must be carefully designed, installed, tested, and maintained to ensure their reliability and effectiveness. In addition, understanding the NEC requirements such as 700.4, 700.9 and 700.12 is important. By following these guidelines, facilities can minimize the risk of injury and property damage during an emergency. Remember, both critical and emergency systems require regular maintenance and testing to confirm operational readiness. Record keeping of inspections and maintenance activities is an important component of this process. Consider investing in professional services for testing and maintenance, particularly if your facility lacks the expertise in-house. Work closely with electrical contractors and engineers who specialize in emergency and critical power systems. These specialists can provide invaluable assistance in designing, installing, and maintaining these systems. They can also help ensure compliance with applicable codes and standards. The coordination between critical and emergency systems and other building systems is crucial. This includes fire alarm systems, security systems, HVAC systems, and building automation systems. Ensure that these systems are integrated and can communicate with each other effectively. In addition, it is vital to have a comprehensive emergency plan in place that outlines the procedures to be followed during various types of emergencies. This plan should include specific instructions for dealing with power outages and other electrical system failures. Conduct regular drills and training exercises to familiarize building occupants with the emergency plan. This will help ensure that everyone knows what to do in the event of an actual emergency. Consider the long-term reliability of critical and emergency power systems when making purchasing decisions. Invest in high-quality equipment that is designed for continuous operation and has a proven track record of performance. Also, plan for future growth and expansion when designing these systems. Ensure that the power source and wiring infrastructure have sufficient capacity to accommodate additional loads. And finally, stay informed about the latest codes, standards, and best practices for critical and emergency power systems. Participate in industry events and training programs to keep your knowledge up to date.